The Guinness Book of Records tells me and my family that the fastest 1 liter of lemon juice has been consumed by a straw, and it took 25 seconds, done by Stephen Deckard II from the USA, and now something completely different. So next, I will be generalizing the treatment of thin film structures, where interfaces now are highly reflecting ones. Of course, the math becomes quite a little bit more complicated, but the nice thing is that at the end, we really have a possibility of making better performing interferometers. And this is essentially what we will be getting out. So we have a possibility of actually getting interferometers out by just taking use of thin film structures. And at the end of the lecture, I will also introduce some parameters that can be used to estimate the performance of such instrumentation. So essentially how these kind of cavities or resonators behave, so that the terminology and the parameters that I will be introducing can also be used to understand how, for example, laser cavity performs or a resonator performs. So this is what I will be speaking today, and let me just get right away started. Of course, the lecture is multiple beam interference, and the chapter is on interference effects. Course is optics. So let's generalize, like I have been promising for many times, our earlier treatment of thin films into a case where we now have several reflections taking place as shown in the figure. And essentially this means that when we start having a high reflection coefficient here at the first interface as well as the second interface, then it's not a good approximation anymore to just assume that light is being reflected once and that's it, and most of light is being transmitted, but rather we need to take into account a possible of redistribution of light. So light is actually being reflected many times inside the thin film structure, and this really changes our treatment. These kind of configuration and these kind of devices, components, situations do not often take place in nature. So for example, not in a tail feathers of magpies, we don't have these kind of structures, but rather we need some engineers that actually on purpose are making these kind of thin film structures. So essentially these only happen when the surfaces are strongly reflecting, and this doesn't happen in nature quite easily, but rather we need to take use of not anti-reflection coatings, but the specific reflection coatings to make the interfaces to be highly reflecting ones. And now when that takes place, we must calculate the superposition of field that is being caused not just by a single reflection at the interface, but rather by several reflections due to the thin film structure. And for conceptual clarity here, this is not actually the case in reality. We assume that both interfaces are identical. So in real life instrumentation, this is actually not usually the case, but I will leave you to solve the change or the modified situation if you ever encounter with a real world instrument that is taking use of thin film structures. Then you're really way beyond of being just a happy participant of this introductory course. So, as before, we are interested in calculating the superimposed field, and especially we start with the calculating the superimposed field into the reflected direction. And mathematically, we can easily calculate that. Looking at the figure, we just need to sum over different wavelengths or rays of light that are coming and being reflected at the interface. So essentially, we need to calculate all these different rays that have been reflected by the interface. And here, since we are interested in superposition field, we are implicitly assuming that we are taking these rays that do not seem to be coinciding in space. So we would be focusing them by a lens into a single bucket detector, and that would be the location, a single point in space where the interference actually occurs between the two different rays of light. What kind of instrumentation we could, for example, use to detect these two different rays or many different rays would, for example, be our human eye. So when we have a collimated bunch of rays coming through at this kind of or being reflected from this kind of thin film structure, if they are hitting our eye, then our eye acts both as a lens and as a bucket detector And there indeed we are seeing the reflected light and the interference effects associated with the detected light. So for example, we can see this right on by our human eyes, or equally well, we could just use a lens and a camera to actually see what happens. Or in principle, also just a lens and a bucket detector. So a single pixel detector. So our problem is to calculate this, and essentially it's the problem of calculating the relative phases of each of these rays of light, so EIRs. R is in reflected ray, and I is standing from 1 to n, so in principle we need to take into account many different reflections. Earlier, we calculated the path difference already for the field of the first reflection, so EIR and the EIR2, so that the path difference between these different rays was the lambda 2,1 was of a form that we had 2 times nt, that's the refractive index of my thin film, times d times cosine of theta t. So essentially we have the film thickness d here, we have the refraction angle theta t, so that would be this angle, which of course depends also on the incidence angle and the refractive index profile of my first medium of interest. So this is giving me the phase difference, so, the kind of optical path difference, big lambda, and then the phase difference will be this times k. And looking at the geometry of the problem, and this is always the beauty of mathematics, not the beauty of mathematics, but the beauty of physics, that we draw a good figure, and then we can learn all we need to learn by just looking at the figure. So we also now see that the same path difference actually takes also place for the ER2 field and the T3R fields. So essentially, we have already calculated the scenario where we had a reflection, and then the ray of light was being transmitted, reflected, and transmitted again, and then we were calculating what is the phase difference of these 2 different rays in this plane of here. And now, by just looking at the figure, we can already intuitively see that this kind of shape here, this is exactly the same shape that we have here. So essentially, we will have exactly the same kind of path difference between the ray 2 and ray 3 when we are looking at the subsequent reflection. And the same thing happens on and on for all the subsequent rays that are being reflected by the interface. So this is what we can really use to simplify things. So all adjacent reflected waves really have a same phase difference, and the phase difference delta is given by the k, the amplitude of the wave vector, times big lambda. So this would be the 2 pi divided by lambda naught, the vacuum wavelength, times the big lambda, the optical path length difference. So delta essentially is 4 pi divided by lambda times nt times d times cosine theta, the transmission angle or refraction angle. In principle, interfaces could give rise to additional phase shifts. So please recall our section on Fresnel coefficients. So if the Fresnel coefficients T's and R's are complex valued, we would have peculiar additional phase shifts associated with these reflections and transmissions. But here, for simplicity, we do not consider such possible shifts, so that we can progress with the conceptually clear situation that there will be just real valued quantities, the R's and T's. And now we can really calculate the reflected total field. So that was of a form that we are summing all these different rays, and now these different rays, EIRs, are given by a first term reflection and E naught here, so that this would be just the original beam of light being reflected once, and here we have the reflection coefficient here once, and then the second ray of light, that's essentially like let me first try out the math and then explain by showing things with the mirror, my what is this guy, arrow, almost like a mirror arrow. So the second ray, I'm looking at this guy here, and what was the field for that? Well, we are being transmitted once inside into the film structure. Then we have another reflection here, R prime here. Then we have a transmission here, T. And then we have the case here. So we have the E naught, and then we have a phase accumulation here due to the fact that the light is being also propagating by this given optical path length. So that's essentially what the phase difference we already calculated. And then the third ray, like we can do the same kind of progression, and I will then go through these terms now with my arrow that then I have here. I have one transmission here, and then one reflection, second reflection, third reflection, and then second transmission. So we have the two times r primes, so that they we are separating the difference between cases of having a reflection either on the actually, sorry, we do not here. Yes, I'm now remembering things better. Sorry about this. So R prime corresponds to a reflection inside the thin film structure, and normal R correspond to a reflection when we are having a reflection when the ray of light is coming from the air and is being reflected at the air thin film interface. And then the same thing is here with the transmission coefficients. So when the ray of light is propagating from air into the thin film structure, we are using T transmission coefficient. And then when the light is being transmitted and refracted from the thin film structure into air, then we are using the T prime term here. And then what we have here is that we have 3 times R primes. So essentially, we have 3 reflections inside the thin film structure. So we have once, twice, and 3 times that. And that's it. That's fine. And then we have 1 transmission into the thin film and 1 transmission out of the thin film. And that also makes sense. Once in, and then once out, and that's it. And then we have 2 times of this phase accumulation. So essentially, this phase difference once, and then the twice coming from here when we are wanting to look at the phase difference felt by all of these rays at this given phase front here. And then the same thing progresses on and on. So essentially what we learn here is that this term r prime squared times exponent I delta is being repeated for adjacent waves. So this is actually being a kind of a systematic trend that we are seeing here in this progression of the terms. So the reflected field, the total field, really can be written as a sum, so that we have the first term, r times E naught, then times this kind of parameter here, or term here, and then we have this kind of progression of these terms that is being repeated in this kind of systematic manner. And this is super nice, because this term inside the square brackets, this term that we have, this is actually a geometric series, and we can then actually calculate this analytically. So we just redefine this term r prime squared times exponent I delta, so that we define that to be S, and then we can write the geometrical series in a very clean fashion, that this is just 1 plus S squared, and so forth. And when we go to do high enough powers, this is essentially 1 over 1 minus S, as long as the modulus of S is smaller than unity, so that this actually converges into this value. And we can really easily derive this, and for pedagogical reasons, I just want to derive it very quickly here. Why not? You can skip this derivation if you wish, so that we have this term here on the left-hand side, and we can denote that this term, we can rewrite it, that we just have some kind of summation term plus Sn term, and here this is equally the case. So essentially, we are taking this term here from the S, and we are taking S to be a common multiplier, and then we are left with this kind of term that looks almost like this guy. So essentially, we can rewrite these things in a way that this summation here is essentially this guy inside the parenthesis, so sigma n minus 1 plus S to the power of n. And this guy here is 1 plus S times this sigma n minus 1. And this is nice, because then we can write this in a more simple manner. So this is 1 plus S sigma n1, and now we actually have an equation that we can even solve with respect to this sigma n minus 1. And now we can solve the sigma n minus 1, and this is essentially now 1 minus s to the power of s to the power of n divided with s, 1 minus s. And when we let the n to go into infinity, tend into infinity, this guy goes to 0 as long as the modulus of s is smaller than unity. And then we see that this sigma actually is approaching 1 over 1 minus s. So we have really simply derived the geometrical series, and this is super simple derivation to be done. Maybe you should even memorize it so that you can then be able to apply it yourself more easily and see it yourself when this kind of math happens. And now we would need to calculate the total superimposed reflected field. But here we do not actually worry more or further about the reflected field and superimposed reflected field, but let's now look more into the transmission field, because in real devices this is more often the case that actually is being measured and utilized in instrumentation based on thin film structures. So let's next calculate the field that has been transmitted through the film, and this is in a way same thing. So now we are calculating the transmitted field, and then we have the different terms subsequently arising from the fact that light is being transmitted in this kind of manner. And again, since they are highly reflecting the films, then we actually have many terms, and each of these wave components of the transmitted wave, they are given by in a simple way or a similar way to the reflected case, so that the first ray of light that there we have then is of a form that the incident light associated with the amplitude of E0 is being transmitted once, and since it's being transmitted from air into the thin film, we use the transmission coefficient T, and then from the thin film into air again, so we use the T prime, and this indeed is the case. And then we have this kind of exponent I phi term here, where this phi corresponds to the phase shift of light propagating from point A to point B. And now the second term, essentially it looks very similar as in before, but now we have some additional phase changes to the two reflections inside the thin film, so r prime squared, and then we also have a phase term due to propagation inside the structure. So phi here corresponds to the phase shift due to the wave propagation from point A to point B, and here in the second term we have r prime squared. So essentially now the ray of light, we are interested in this ray of light. So the original ray of light is being reflected once and twice, so that's why we have the r prime squared. And then we also have the propagation inside here that gives rise to the phase difference that actually is exactly like we have already solved for the case of reflected light. And that also explains to you why on earth did we have to start with the reflected light, because if you're only interested in the transmitted light, well, we had to somehow calculate this exponent I delta term here, so why not go through the whole glory of things and actually solve the case of reflected light first. So again, we see that the specific term is being repeated. So again, we are forming a geometric series, and that actually allows us to very self-consistently solve the problem when n tends to infinity. The calculation of the total field will be as before for the reflected field, and essentially we will have a superposition field ET. So that would be the full transmitted field that we would measure as long as we are focusing down, we are collecting with the lens and focusing down all these different rays of light into a single observation point where they are actually interfering. So this is what we need. And this is what happens with our human eyes, for example, when we are looking at these kind of structures. So the ET equals 1 minus r squared times E0, the amplitude of my incident ray, times exponent I phi, phase accumulation from point A to point B, and this is divided by 1 over r squared times exponent I delta. So the transmitted irradiance, we can also simply be calculating this. So we just take this to be the proportional to the modulo square of my field, and now we can calculate the irradiance ET to be a E0 times 1 minus r squared, and this whole thing squared, and then we are having 1 plus r to the power 4 minus 2 times r squared times cosine of delta as the denominator. So I do not do the calculation, but you can verify it yourself that this very easily follows. Just remember that these exponent terms, when we take the modulo square, their lengths will be unity. So essentially they are drawing circles in the complex plane. So that really helps calculating the modulo square values of them. Energy is being conserved in an ideal situation, so that when there's no losses in the case, and this is what we are considering here. And in this case, the calculated irradiances really fulfill the scenario that the total irradiance that is coming into the thin film structure must be the total reflected irradiance plus the total transmitted irradiance. So all of light either is being reflected or is being transmitted. And this works out as long as we do not have any losses. So that, for example, the smoothness of my thin film structure is nice, so that there won't be any kind of diffuse scattering in the different directions, and there's no losses related with absorption of the thin film structure, for example. And most of the time we can assume that this would be the case. There's no losses in the system of interest. And let's now look into the irradiance distribution, and let's now look what kind of parameters are affected by the irradiance distribution, and how we could modify the irradiance by really modifying the parameters. So let's look at the parametric dependencies of the IT, the transmitted irradiance. And this was, of course, of the form that we had already discovered. And let me now write the cosine delta term, the phase term, differently, so that we can also take use of the de Moivre's equation and the trigonometric identities, so that cosine delta can be written simply as a 1 minus 2 times sine squared of delta over 2. So this is already that we discovered in the chapter 6, if I recall correctly. And now the denominator can be reduced into a slightly cleaner form, so that this, the downside of the fraction, 1 plus r to the power 4 minus 2 times r squared. So this we can now write to be a 1 minus r squared to the power of 2. And then we have the leftover sine squared term there on the other part. And this is, of course, equal to this. So essentially we're just like writing things together, so that these three terms can be simplified to be like this. And the nice thing here is that then we have something on the denominator that looks like this, and lo and behold, we have exactly the same kind of term here on the numerator, so that the things become easy in terms of simplification. So we have the transmitted irradiance, so it's I naught, the incident irradiance, times these different terms, and now we can really divide all of these different terms in the fraction with this term we just realized, and then we can simplify things so that we only have a unity on the numerator or on the top side, and then we divide this sine term with this term, and this is what we already now left here. And because of the importance of these kind of functions, this even has a specific name. So this kind of function is known as an Airy function, and it has a different calligraphic symbol here, strange capital A, to denote that this is an Airy function. So we can now write the transmitted irradiance simply as an incident irradiance I naught times Airy function. So we have this kind of very, very wiggly looking A figure here. So the term 2 times r divided by 1 minus r squared, that we can also define that as an f, and this is known as the finesse coefficient. And this finesse coefficient is actually a quite useful parameter, because it tells about the kind of performance and the properties of these kind of resonators. And this, in fact, is essentially like a resonator. So we have the transmitted irradiance, and this is of the form I already went through these, so I do not re-explain myself. The only thing new here is that we have used f here, the finesse coefficient, inside here to simplify the equation. And the finesse coefficient, let me repeat, was defined like this. So it's the square of 2 times r divided by 1 minus r squared. And this r, of course, is the reflection coefficient associated with my thin film structure. So now when we can adjust, and we can, of course, if not by ourselves, but our engineering friends, we can really adjust the Fresnel coefficient R, and we can really now modify how narrow peaks we actually have coming or associated with our thin film structure, associated with the resonator formed by using thin film structure. And this essentially happens when the phase term is being adjusted. And when we are adjust the phase term, then we are more quickly seeing a peak formation. So when we have constructive interference. And the phase term, when it is being changing, delta, then that was given by k times lambda, so that we see that we are measuring peaks peaks in the transmitted irradiance profile of my incident field. So the phase difference is given by this, and essentially what the finesse coefficient now tells us that if the reflection coefficient is low, so that the overall finesse would be, for example, let's say 5, then we are getting a spectral properties resembling something of an A figure. So that there's an x-axis, we now have the phase difference delta here, and y-axis essentially is our Airy function. So essentially that would be somehow related to our transmitted irradiance. And if the finesse coefficient of our thin film structure is low, then we have quite broad resonances, quite broad peaks in the irradiance distribution that we are measuring. And now if we increase the finesse coefficient, so increase the reflectivities of the thin film structure, we are actually narrowing down the peaks very much. And now we are seeing that we're actually having narrow peaks, and these would be the subsequent peaks when we have the phase accumulation, an integer of 2 pi, and then a 2 pi plus 1 here. And this is the nice thing, but in this lecture, I will not spend my time in explaining why this is nice and why this actually is important in some applications, but indeed it is. My point here was just to show you the parametric dependencies, what are the different parameters associated with these kind of structures that dictate how does the irradiance distribution look like. And now we know that if we adjust the finesse coefficient, so essentially the reflection coefficients, we can really modify how narrow or how broad peaks I'm really measuring. And we have defined the Airy function, which, because it has its own name, probably you will be encountering that function many times during your studies and during your life and long journey, so that please try your best to also remember what that roughly looks like. So now I'm at the end of my lecture. I thank you for your time. And please join me quickly in the next lecture, where I will be hopefully being able to elucidate to you better why we care about the peak width, and why, for example, in some scenarios, these kind of narrow peaks are way better in terms of the performance of an instrument than these kind of broad peaks. But more on that, of course, in the next episode when we are speaking about Fabry-Perot instrumentation. So thanks for your time and have a good day.